Welcome back to the complex analysis course. So, in the previous few classes we understand interesting aspects of the analytic function. So, fz is an analytic function and fz is u plus iv. If it is analytic, then ux is equal to vy and uy is equal to minus of vx. This is the essential condition so that the function is analytic. Today we will, since the analytic function is now well defined, we will go to the next level in complex analysis, which is important, and that is complex integration. Complex integration. So, normally what happened in normal integration, that if we have a function fz, fx in real case, so x is changing like this and this is my fx. So, I will just calculate the area under this curve because it is changing, and every time I will calculate this quantity, and as a result whatever I am getting, some limit say a to b, I am having some value here. In the complex case also the things are similar. Fz is equal to, fz is my complex function and z is x plus iy. Now, here x is a parameter, single parameter that is changing from one value to another value, and as a result I am getting this integration in this form. On the other hand, here z can be changed like the variable x is changing, but there are two variables are associated with that. So, two variables should change independently, and as a result z will going to change, and because of that fz is going to change, and then we will have something in the integration form. So, we can do this in the parametric way. For example, t is called the parameter, x and y both are changing with the parameter t. So, t is some parameter, say it is this value. Then if I write this quantity, that means I am having the integration with t, because t is my parameter here, t is changing. Here z is function of t, x and y is also function of t. So, delta z, since z is a function of t, so delta z can be represented as z prime t delta t. So, z prime t delta t, if the z as explicit form of t is known, then I can find out this quantity. So, this quantity is essentially then f z function of t. If x and y is given as a function of t explicitly, then I can write this and replace this, then my integration we only depend on t. X and y if given as the explicit function of t, then I can do this way. Anyway, another aspects of this integration is in the complex plane. For example, for every time the segment wise, the way we just do for the real case. So, the z is something changing like this, and there are small segments say z0 to z n, there are n different segments and it is changing like this. For this is x and y, for different x and y value I will have different z values. So, it is now x and y change independently. If it depends on some parameter t, so x and t will be x, say x is a function of t and y is a function of t explicitly, then there should be a relationship between x and y, and based on that we can draw this curve, that is the thing. But even though they are changing independently, so they are giving some value z1, z2, z3, they are small segments of value for the small increment of x and y together, and I will have one individual value like this, which is forming a curve. Here say zk, here zk plus 1 and so on zn. Now, in between zk and k plus 1, I assume one value say phi k, and this phi k, for this phi k I will have the functional value k. I just construct the formation of the integration. So, integration is just, I am just taking this phi k every time multiplied by zk plus 1 minus zk with a summation k 1 to n, and I call this summation as Sn. So, this is the form I am going to use. So, I am just changing this value to this value, then in between this value to this value I have one value say xi k, and this xi k, if the function is giving to me, I put this function xi k and then multiply, I will have something, and then every time for every point I can have the same thing, and if I sum over k, then I will have something Sn. Now, if these points are too close to each other, then I can write these things as when the limit n tends to infinity, that means I will have the segment infinite number of segments. So, this distance is infinitely small, then this quantity I write it now delta z k. Now, this quantity converted to a integration with the limit say some value, initial value to final value, say a to b, like this. So, this is over some line, because I am taking the integration like this. So, instead of putting initial to final, I should write it is over some line C, like this. If the line is different, obviously this value is going to change and I will have something different. This is called the line integration, by the way. I will have a line in complex plane and I try to integrate my function over this line, and when I try to integrate that, I will have this kind of form. Okay. After having this, now let me give you some idea about this kind of integration, but before that I need to cover one important thing also. So, fz in another form, I mean how this line integral, I mean how I do this calculation. Fz is u plus iv and z is x plus iy. Procedure is straightforward. So, delta z is dx plus idy. So, integration, whatever the integration is given to me in the form fz dz it will be this line integration f z is u plus I v and it is dx plus I dy I will have u dx minus v dy plus I integration of v dx plus u dy. If the function is giving to me, I know what is my u, what is my v, then I need to put that, and then based on the, if the curve is giving to me, I know how this dx dy will going to change, and then I will evaluate the entire integration using this. This is the procedure or the recipe to calculate the integration, apart from any other I mean theoretical detail. So, this is the way we will do the all the calculation, that is why I show. But now one important thing I need to say about, so this is my complex, this is the plane I am talking about, I am saying that this is my line. So, this is the line over which I am doing the calculation or integration whatever. Now, in some cases we will need to close this line. So, I will just integrate over some closed line like this. It is possible because this is a line, I go and then return back. So, it is a close, something close. Now, this form a region. So, this line, whatever the line which is closed are encircling some region. This is the region, is encircling. This is called the region. Now, this region is connected by a single line. This is called, this region which is connected by a single closed loop or something like that is called simply connected. I will come back to this thing in more detail, but since we are dealing with the integration line and region, it is better to just introduce how these things are working. So, it is a simply connected region. Why it is simply connected? Because if I want to shrink, so this is the region given, I want to calculate the integration, and this is say my closed loop inside the region. If I want to shrink this region, shrink this curve, I will have a point here like a rubber, it will shrink and it will come to a particular point without leaving this region. If that is the case, then this is a simply connected region, but it is not always the true. I will show you another example. That means, here my z is, if this is some point z, so mod of z for example is less than some value big value r, if this is the radius r. So, this is the region, this kind of region where I can have a closed loop, and if I shrink this closed loop inside the region and come back to a particular point without leaving the region, then this is a simply connected region. But as I mentioned, this is not always true. So, let me draw another region enclosed by two closed curve like this. So, now my region is this one, this is the annular region, and you are aware of this annular region because in the previous class we show, and the say z is okay, I mean here z point is here. So, here if I say this is my z point, so z is less than r greater than small r. So, if this is my small r, if this is my big R, so this is the region I am talking about mathematically, which is given like this. And now, if I draw one like this, this is the closed curve I am talking about, say big gamma. So, this region is not a simply connected region, because if I have a closed loop inside the region and if I want to shrink that, it will not going to shrink a particular point without leaving the region. So, this is called the multiply connected region. We will use that in the future class, but today just I will show you what is the difference between simply connected and multiple connected region and the idea of that. Multiply connected region. Okay, so far we have learned something about the line integral. However, the line integral calculation we did not do, we will do shortly, and also know that if the line is closed, then I will have a closed kind of loop, and there also I can integrate, and this loop can be associated with certain region. In some region it is multiply connected, in some region it is simply connected, and based on that I define that which kind of integration I am talking about. It is a multiply connected region or is a simply connected region integration. So, we will do these things later, and then it will be helpful for you. This very brief introduction will be helpful for you about the region and all these things. So, now let us directly go to our original the problem I started with, that is the line integration. So, let us take one example. So, let me give you one example about the line integral. So, okay, the first example 1, line integration. How to do that? That is the thing. So, for the line integration, first thing that a contour should be given to you. So, it is the real integration. First I start with the real integration, and the integration is given to you something like this: x y dy. Suppose x y dy, this is x y is my function, and I want to find out this is the region. That is why two variables are associated with that, exactly like the f z. And here I want to integrate, say, from point 2 0 to 0 2 over this line. This is my x, this is my y over this line. So, the thing is that here when I do this calculation, if you try to do this calculation, you need to know every time how they are related. How they are related, you need to know what is the relationship between x and y, because you need to put these things to a single variable that I show just in the previous derivation. So, we need to use some kind of parametric variable to understand how this is changing. So, here the parametric variation is x, say function of t is my parameter, is such that 2 cos t and y t is 2 sin t. As I mentioned, my x and y should be the explicit function of t if t is my parameter. Here I wrote these two things in this way, these two variable, to make it a single variable. So, now you can see that when this point, which is 2 0, is essentially means x is equal to 2, y is equal to 0. X is equal to 2 means my t here is something like x is equal to 2. Okay, let me change it to sin t and cos t. You can do that with cos t and sin t, no problem with that, but your limit will go to no, it was initially it was, I think it was correct, because when my theta is 0, yeah, cos t sin t, it is fine. I mean, when my theta is 0, that means t is 0, t is behaving like a theta here. When t is 0, then x is 2 and sin y is 0. When it is 90 degree, if t is behaving like a theta, if it is 90 degree, then what happened, x will be 0 and y will be 2. And also this is a part of the circle. So, the relationship between x and y is already we have is equal to the radius here is 2. So, it is something like this. If you calculate from this parametric variation, then you will get back to that thing also. Okay, so what is my dy then? 2 cos t dt. If I make the dy, then it will be something like this. So, what is my integration then? Now, this is defined because I am changing one variable, and now t is changing from 0 to pi by 2. If I want to write in form of t, x y is 2 into cos t, 2 into sin t, and dy is 2 into cos t dt. So, this there are many 2's are here. So, 8 integration 0 to pi by 2, I will have cos square t into sin t dt. This one. Now, I need to change, say I put cos of t as another variable p. So, sin of t dt is minus of dp. If I take a derivative of cos, I will have minus of sin of dt. So, I will put as minus dp. So, if I change, it will be cos square means p square, sin square dt is with a negative sign dp. Now, again the limit will going to change because now I am doing that in terms of p. So, the limit when t is equal to 0, p is equal to 1, and when t is equal to pi by 2, p is equal to 0. This negative sign now going to absorb. So, if I do directly, it will be 8 p cube divided by 3, 0 to 1, which is seems to be 8 by 3. I will have this value something like 8 by 3. Now, if the path is changed, I am not going to go from here to here in this way, but in different way. Should the value of this quantity will be same, the standard answer says, I mean say may not be the same thing. Let me do that. So, now what I will do, I will go from this point to this point in this path, I will change the path. If I change this path from this point to this point, then this integration c is now changed. So, in first case, if this is my c1 path, it is c2 path, I calculate that c1 xy dy comes out to be 8 by 3 when the path is defined like this. Now, I am doing this problem xy dy. Now, try to find out what should be the value of these things. Since you have already done these things, I believe it is straightforward to you to find out this. So, what is the relationship between x and y? So, x plus y is 2. This is the relation here for this red line. Every time if I change x, y is changing, and the relationship between x and y should be 2. When x is equal to 0, y is equal to 2. When y is equal to 0, x is equal to 2. So, this equation gives you the same thing. So, now what I will do, now things become simpler. I will just change these two here. I just replace x in terms of y. Also, now since it is a single variable now, and I know what is the path, now I can put my limit here. So, what is the limit of y? I am going from here to here. So, limit is y 2 to 2, 0 to 2. So, now this if I do the calculation, one y multiplication is there. So, I need to multiply that also. So, it will be 0 to 2 2 of y minus y square dy, which is 2 y square by 2 minus y cube by 3 with the limit 0 to 2. This 2 to cancel out. So, I will have something 4 minus 8 by 3. So, it is 3 into 4, 12 minus 8. So, 4 by 3. So, for C2 the path C2, this value is now different. So, there is a for C2 C1 this value is this, and for C2 path this value is seems to be 4 by 3. So, today I would like to conclude here, because in the next class is a very simple example how one should do the line integration in the real case, but imaginary calculation will be equally same. It will be exactly the same way we have done here. Only thing is that one I will be somewhere in the expression, only that is the thing, and the variable that the way it is vary x and y will be same, because there also we will do the same thing, x and y, it will be varying in this way. So, next day we will try to find out that here one interesting thing I find, that for this particular function in real case, if I go from this path to this path and calculate the line integration, and if I go this path to this path and calculation the line integration, the result are not same, even though I am reaching the same point, starting from the same point to reaching in the same point. But in complex analysis we will have a very beautiful thing regarding that if the function is analytic, then we will find that it is irrespective of the path you are going. If we try to calculate the integration, line integration of an analytic function, we will show that it will be independent of the path. That is a very interesting outcome that we will have for analytic functions specially, and we also try to prove that it will be independent of the path, rather depends on only the initial and final points. So, with that note let us conclude that. So, see you in the next class, where we again discuss this line integration, but using some kind of complex variable. With that, thank you very much for your attention.